Okay, so plan today is to try and get through the remainder of the Poisson distribution. We are going to move it on to connecting up the binomial and Poisson models. So the Poisson distribution is a way of estimating the binomial distribution as well. We can use that to estimate a binomial problem, which we will have a look at towards the end of the session. Now, before we do that, one thing that we do need to consider is the mean and variance of a Poisson. Now, we had to do that for binomial. If you remember, the binomial E of x, expected value of x, was n times p, whereas the variance was n times p times q, or np 1 minus p. For the Poisson distribution, it's a lot easier, okay? Because it turns out that for any Poisson distribution, the expected value and the variance are both the same. And they are both the same as the rate. Now, just thinking kind of logically about that, right? If you say that the rate of cars that are passing you, okay, in a 1 minute period is, let's say, 3 a minute, then how many would you expect to pass you in a minute? 3, right? So it makes sense how that would be the same as lambda. Now, the variance is always going to be a little bit more fiddly to explain, okay? The variance showing you how spread out the distribution is. Now, that, as we've seen, okay, as the, if you remember from last lesson, as we increased the value of lambda and we drew out the distribution, the central bars that were the largest moved towards the right as lambda increased, okay? Can you remember that? So if we go back to this, okay, so as the lambda increased, the bars did shrink, okay, but the largest bars were always moving to the right as it increased, right? So as you can see, as lambda is increasing, the spread of the bars is also increasing. They're getting more and more spread out. And they are following this variance of lambda. So as lambda is increasing, the variance, the spread of the distribution is also increasing. Okay? So you can kind of see it visually. I'm not going to go through the derivation of it here. You don't need that. Plus, in the formula booklet, you are given this information. So where the majority of you have been looking for the formula, okay, so on page 9, where the Poisson distribution is given to you, the formula, you'll see the two columns mean and variance, and they're both lambda. Okay, so there's no reason why you would forget that bit of information. Okay, so what you can now do is you can now think about if you were given a model and they'd estimated or they figured that the mean was 12 and the variance was 3, is this likely to be a Poisson distribution? Well, no, because now you've got a way of identifying in a practical context, does the mean and variance, are they close to one another? If they are, then you could potentially model it using a Poisson. If they're not, then no. Okay? So you've got this additional thing to consider. So I would definitely take note of this, okay, as part of your notes, that you are saying that if the mean and the variance are close, then the Poisson distribution is likely to be a valid model. Okay? It's one of those little questions again, those little 1-2 markers to consider. Taking that on board then, the Poisson distribution questions that you were just having a go at are very much kind of like the basic find the probabilities, okay? You also need to do it in a more context problem-solving way. So I'd like you to spend, let's say, 10-15 minutes on this set of questions that are further on in that exercise. Okay, right. So what you've seen from a couple of those problems is a useful thing to be aware of, in that if you were said, let's say we go back to that example of watching the cars pass by you, and you're recording it, and you find that you're getting a constant rate of, let's say, 2 every minute. So you'd be able to write down a Poisson distribution where lambda would be 2, okay? And then the question in the exam says, what's the probability of having 100 cars pass you in an hour? Okay, so this is 2 every minute. So you could multiply your rate by 60 to work out, right, so it would be 120 cars that I would be looking at and finding every hour, and then I could find the probability of getting over 100. Okay, so that is kind of a similar idea to that wombat question that you were just looking at. Okay, the idea that that rate, considering lambda as a rate and then applying it to the context. Now, with that as well, we can look at combining 2 or more Poisson distributions to solve a potential problem. So for example, let's say we had X representing the number of vehicles travelling into a town at 3 p.m. where the rate is 3.5 per minute. And then we have another Poisson distribution where we say that Y represents the number of vehicles travelling out of the town at 3 p.m. and that's 5.7 per minute. Okay? What you can then do is you can form a third Poisson distribution, let's call it T, and this could represent the number of vehicles travelling in either direction at 3 p.m. So you can write it as T being X plus Y, which is a Poisson distribution of 9.2. So it's just combining those 2 rates. Okay, so I've got 3.5 going one way, 5.7 going the other. So in total, it would be 9.2. So it's as straightforward as that, combining 2. So in general, if we wanted to do this in general, we could say that if X, let's just erase that bit. So we could say that if X is a Poisson distribution with rate lambda and Y is a Poisson distribution with rate mu, then we can combine the 2 Poisson distributions, and the rate for this Poisson distribution will be lambda plus mu. Okay? So it's a pretty straightforward extension of what you've already been considering. So if we have a look at an example of this, let's say we've got this rare disease which causes the death on average of 3.8 people per year in England, 0.8 in Scotland and 0.5 in Wales. As far as is known, the disease strikes at random and cases are independent of one another. Now, depending on what the situation would be, if it was like a virus, then it probably isn't going to be a Poisson distribution because it's likely being spread. If there's no kind of spread, if one person getting it does not affect another person getting it and it's independent, then a Poisson could be used in this case. What is the probability of 7 or more deaths from the disease on the British mainland? Okay, so what we could do is we could combine each of these rates, the 3.8, the 0.8, the 0.5, into a single Poisson distribution. Okay, so 3.8, 0.8 and 0.5 all add up to 5.1. And then what's the probability of 7 or more deaths? So greater than or equal to 7. We do 1 take away less than or equal to 6. We can look that up in the tables. And so we get 0.2526. Okay? So that is quite a straightforward kind of example, just combining the Poissons together. Let's have a look at another one. On a lonely highland road in Scotland, cars are observed passing at the rate of 6 per day and lorries at the rate of 2 per day. On the road is an old cattle grid which will soon need repair. The local works department decide that if the probability of more than 15 vehicles per day passing is less than 1%, then the repairs to the cattle grid can wait until next spring. Otherwise, it will have to be repaired before the winter. When will the cattle grid have to be repaired? So, the repairs will have to be left until spring. Questions? What questions might be raised about the model? Were there any kind of problems with the model, do you think? Right, okay, so, you know, being this lonely highland road, it's unlikely that you just get random people just going past this road. It's probably, or it could be, one where the people that use that road are just people who live locally. It might be the road going up to somebody's house, for example. And so it might not be a random selection of people that are actually using it. So these kind of considerations we've got to think about. So is it a case of there being regular users? Would this have a difference? Would this have a difference upon the calculation? Is it true that every car or lorry travels independently of every other one? Not necessarily. Okay, one might be following another in this case. Other vehicles aren't included. Okay, there may be a reason for this. Bicycles, motorcycles, depending on the cattle grid, might not want to drive over it. Okay? So, these kind of queries and questions you might have to think about when dealing with a Poisson distribution, and think about the context of the problem. Okay? So keep it in mind. Right, I'm going to miss over that. We're going to move on to estimating or approximating a binomial with a Poisson. Okay? We know that a binomial distribution has 2 parameters. It's got the n and the p, the number of trials and the probability of success. The Poisson distribution only has 1 parameter lambda, the rate. Now remember, if the Poisson distribution has an expected value that is the same as lambda, we can estimate lambda using n times p, because that's the e of x for a binomial, and that's the e of x for Poisson. Okay? So this works if n is large and p is small. So there is a great many trials, but the probability of the event happening is low. Now you might be wondering, well, how large is large and how small is small for the probability? Okay. Now it's a bit hand-wavy. Okay. Because this is an approximation, the situation is that if if you've got a relatively large n and p is small, then your Poisson distribution will fit the binomial fairly well. The worse that condition is, okay, the closer these are together, then the less likely your Poisson will estimate it, okay, and approximate it. So what we're going to do is we're going to look at a particular problem. So here is the situation. Let's say we've got a factory packs bolts in boxes of 500, and the probability that a bolt is defective is 0.002. Find the probability that a box contains 2 defective bolts. Okay, so our first method would be to use the binomial distribution. Okay, so method 1. So for this problem, we would have a binomial distribution where we've got 500 as my n, and the probability of a bolt being defective is 0.002. Okay? Find the probability that a box contains 2 defective bolts. So the probability of x being equal to 2. Okay? So this would be a calculation that has 500, choose 2, times by the probability of a bolt being defective, and I want that to happen twice, times by the probability of a bolt not being defective, and I want that to happen 498 times. So 500, choose 2, times 0.002 squared, times 0.998 to the 498. Okay? So, well, let's, if we do the calculate display, then we can kind of have a better look at how close these are. 1841238752. Okay? Right. So, Poisson. Let's do method 2. So for method 2, if we have a look at the situation, n is large, p is small, okay? We've got relatively large n, the probability is quite small, okay? There should be 0.002, shouldn't it? Okay, let me just change that. 0.002, there we are. Okay. So, n is large, p is small. So what we can do with our Poisson is to say, well, lambda is equal to 500 n times p. So we do 500 times 0.002, which, lo and behold, is 1. Okay? So we want the probability of x being equal to 2, which is e to the minus lambda times lambda to the power of r over r factorial. So we pop that in the calculator. we get 0.1839397,206. So to 3 decimal places, they're the same. Okay? They're not perfectly exactly the same. However, we have got a reasonable estimate or approximation using the Poisson distribution. Okay, so here are the two numbers side by side. Now you might be wondering, well, why would you do this? Why would you actually work with the Poisson distribution in order to do it? Because if we don't have like the Casio class whiz, right, and you're using the tables to do a binomial distribution, right, we don't have tables that go up to n is 500. However, we do have tables that work for 1. Now, obviously, that we only got 1 because the 500 and 0.002 multiplied together make a nice number that were in the tables that we had. But in the grand scheme of things, it usually makes the calculations a little bit easier to work with. Let's say we've got this question. Find the probability that at least 2 double sixes are obtained when 2 dice are thrown 90 times. So I'd like you to have a think about this problem with the person next to you. See if you can figure out how you might go about it. So what's the probability of getting double six? 1 over 36, okay? So we can use that. Okay? So that's the probability of success, right? And you're doing the trial 90 times. Okay? So that sets up a binomial situation. So once you've got a binomial distribution, you can change it and approximate it using a Poisson, right? So you've got 90 trials. Probability of success is 1 over 36. So we can approximate it. We can approximate our lambda. Well, we can get the lambda by multiplying 90 by 1 over 36. N times P. Okay. That's 2.5. So then you can approximate your x with a Poisson distribution. And if you want at least 2, we should be able to get 0.7127. So we're going to finish off looking at these 3 groups of questions on page 23. There is an extension question here, which is a type of problem that has cropped up a couple of times on past papers. So you need to be thinking about setting up an equation to solve with that one. Okay? So page 23, to finish off the Poisson distribution, okay? You might want to have a go at that question as well. You might be wondering, okay, from that n is large, p is small thing, another identifier is that if you multiply the n and the p together, that in itself is not too large. And what you generally say is that should be less than or equal to 10. Okay, so in order for this kind of process to work, you usually go for about n times p is less than or equal to 10. In recapping then, to make sure we're kind of fully aware, and you know, one of these would be very good as like a little revision card or something that you've got as a memory aid. Going from binomial to Poisson, to approximate a binomial using a Poisson, it must fit these criteria. So n must be large, p must be small, and you're looking for the product of np to be less than or equal to 10. Now, in order for you to go from the binomial to Poisson, you must calculate the parameter lambda by multiplying n and p together. This picture will get bigger because once we've learned how to do the normal distribution, we can use the normal distribution to approximate either a binomial or a Poisson. Okay? However, because the normal distribution is continuous and these two are discrete, there's a little bit of fudging involved using a continuity correction. So some of you tried this question on the board and got to the correct answer. The idea was that in this large town, one person in 80 on average has blood type X. How many donors must be taken at random in order that the probability of including at least one donor of type X is 0.9 or more? It's quite a complicated question to ask. The idea is that we don't know what n is. If we were going from a binomial, we've got a probability of 1 over 80 and this n that we need to find. So we can approximate using the Poisson to say that lambda is n times p. So this is what you need to get from the words. The fact that we've got the probability of including at least one donor is 0.9 or more. Now this side left-hand probability is 1 take away the probability of x being 0. With rearranging, you can subtract 0.9 from both sides, move the probability of x equals 0 onto the right-hand side, muddle it around, and you can get it to this. Now, with the probability of x being equal to 0, you can substitute everything that you know into the Poisson formula. It's just that what you'll get is n over 80 to the power of 0, which is 1, divided by 0 factorial, which is 1. So it's just that. Then you can use logarithms, logging both sides. So that n must be greater than or equal to, because you're multiplying both sides by minus 80. So the inequality flips around. Minus 80 log 0.1. And so n has got to be greater than or equal to the 184.2. So the next n along that works for would be the n is 185.